Hello, this is Manuel Valera, and my project is about machine learning-based prediction of dissolved oxygen in a small coastal embayment. Dissolved oxygen is a fundamental quantity that we usually want to track in water. However, it's actually very hard to model in coastal regions where the relationships become highly nonlinear. So the goal of this project is to be able to take indirect measurements of dissolved oxygen by using very basic thermodynamics variables. So far, this kind of regression has been very hard to do, and we are proposing to use machine learning to get better results. And we expect this workflow to be applied both in sensor development and numerical post-processing to actually estimate dissolved oxygen in a indirect manner. So we have found data from the San Luis Obispo Bay, and we have two sets of data. One is offshore, here seen, and the other one is nearshore. The difference between them is that the offshore is still linear, somewhat linear in the relationships, while the nearshore is very diffuse and highly nonlinear. We can see that easier in our correlation plot. This is a Pearson correlation matrix, and we can see the offshore set is still correlated between the different features, and the nearshore matrix is very low correlated. So the results that we got is by using support vector regression and random forest regression are actually very good. So for the offshore set, we got an R-squared error of 0.99 and 0.98 in random forest and SBR respectively. And the most important features were, in this case, temperature, salinity, and depth. So remember, this is a linear regime. But the highly nonlinear region, which is the nearshore, although it's very hard to model, usually with our approach, we can still get 0.98 and 0.94 R-squared error of the estimation. And in this case, now time becomes the most predominant or more important feature, followed by temperature and salinity still. But in contrast to the offshore estimation, the depth is the least important now. Additionally, we also wanted to know how much of training data we could actually use to train the model to get a good enough approximation of dissolved oxygen. And we have found that if we use time as a predictor, then we can get away with only using around 4% of the data to get more than 0.9 R-squared error. But if we don't use time, which as we remember was the most important estimator, we have to go all the way to 15% of the training data that we started with. So the importance of this is that we can actually use a very small data set to predict a very relatively big testing data set in the nearshore region. So in conclusion, we have found that both random forest regression and support vector regression can successfully estimate the dissolved oxygen content in nearshore coastal waters with basic variables as the predictor. In any case, random forest outperforms SBR, and this is probably due to the more robust non-linearity of random forest. Uh, Also, we found that we need little relative information to get very robust predictions, and we see here. And we basically conclude that machine learning can actually help overcome highly nonlinear regimens, such as the one that we're studying here, both in experimental and numerical setups. And for further work, we will explore artificial neural network, time series forecasting, and machine learning processing modules for numerical models. Thank you.